All right then, welcome. Today's lecture is the most important lecture in this course, and probably the most important lecture that you've done in all your physics degree. You may or may not agree. I want to talk to you today about a topic that I mentioned in the previous course, namely renormalization. And I want to explain what this thing is, why it's relevant for doing physics, and how do we do it in quantum field theory. So I've already explained the basic ideas in the previous semester. I'm going to go over those ideas again. And then we're going to learn how to implement these ideas within quantum field theory. And we're going to discover an amazing result that says this process works for certain quantum field theories. But before we do that, I want to go back to basic physics and how we actually do physics. You know, how is progress in physics? How does it take place? How do we make progress? How do we do physics? So it starts with observations. We become conscious, we make observations, we acquire empirical data. You're born, you become conscious, you collect empirical data about the world. And at the beginning, it's like a list of unstructured data, just numbers or however the data is that you collect your data, however it is represented for you. You get this list of empirical data and you try and explain the data. That's your second step. All the while you're receiving observations, all the while you're learning that if you do X, then Y happens. All these are observations. They give you this list of data, and this list gets longer and longer and longer as time passes. And then you learn as you get older that you can benefit from other people's lists of data. There's quite large treasure troves of data that people have collected from all the physics experiments of all time. And you want to explain that because at the beginning, the best explanation you have when you only have a few observations is just the data itself. But after a while, the data collects and you get more and more, and this list becomes harder and harder to memorize, and you want to find a simpler way to compress this data. So if you like, explaining data is kind of a form of data compression. You have all this observational data, you don't want to remember all of it, so you want to compress it. You want to make it easier to store without having to just remember the whole list. Now, in physics, we've developed some pretty sophisticated data compression algorithms. Now, one perfectly valid way to do this is the full operationless way to do this process, would be simply to use some information theoretic data compression routine and literally pk-zip all the observational data that you've ever received. That's as good an explanation for everything you've seen as any other at this point. But it's not very simple, right? What we're after is we were after understanding. We want that our data compression routine, whatever it is, confers to us understanding about the data we're receiving. We don't want a list of near completely random variables that is given to us by a compression routine. We want to understand the data. Okay, I don't know why we want to understand the data. I guess in evolutionary terms, there's some pretty good reasons why you might want to understand all the observations. You know, you'll be fitter and you'll be better able to avoid your predators, and you'll be better able to catch your prey if you understand the world around you. So there's an evolutionary reason to want to understand things, but on a more deeper philosophical level, I don't know. But that's what we want, right? We want understanding. So understanding is a kind of data compression, ultimately. We're going to look for some way of generating or storing all the data we've received so that we can not have to look at the list every time we want to understand what an experiment will do. And for us in physics, there's sort of, with our human biases, there's a great variety of ways to actually understand data. And I'll list for you a couple. So you might say you've understood the data if you can assign some Hamiltonian plus Hilbert space to that data. You might say that you've understood the data if you can find some neural network that can reproduce it. You know, you do some kind of machine learning. Actually, I wonder if in 100 years when we give lectures on physics, whether or not neural networks will have been promoted to a higher level on this list here. At the moment, it's very sexy, right? People are using neural networks and machine learning to do all kinds of things. And, well, you might just take some Bayesian kind well, this is, if you like, a subset anyway. Well, let's just go back to the list of the data. That's a possible way to understand it. Now, we have a strong prejudice in physics towards this way of understanding the universe. And I'm not going to go through the history of physics with you. You know why we ended up here and all the intellectual debates that took place on the way to getting here. We understand now that the universe is quantum because that was one of the best ways we found of explaining all the data that we've received. Very, very compact way of expressing that data. Now, that's the purely explaining what I'm seeing around me part of physics, but there's one other part of physics, and this is also very important in evolutionary terms. In fact, that's why we're doing all of this in the first place, and that is we want to predict. We want to make predictions. It's very important to make predictions. You start observing the mountain lion, and then you want to predict where the mountain lion is going to go so that you can avoid the mountain lion. You don't want to be eaten by the mountain lion. So you want to make predictions. So you do some observations, you explain the data, you try and understand the data in some way, be it via data compression all the way through to maybe coming up with a Hamiltonian. And then you try and make predictions. And one prediction is if I stay away from the mountains, then I won't encounter mountain lions. So this is the key part of doing physics, the why, is we're going to explain what might happen. If we make a new observation. In physics, we cannot, and in general statistics, you cannot confirm a hypothesis, you can only reject a hypothesis. So we're going to make predictions means we're going to formulate a hypothesis that we wish to reject, not one that we wish to confirm. This is a key point. All right, that's physics. That's how we do physics. And then there's one super important step that I just neglected, and that is if we just stop there, and we'd all probably be dead, we have to do something here. We have to go back to step one. And this process, we iterate through this process as time passes, formulating hypotheses, rejecting hypotheses. And if we believe, as we do, that the right way to the most compact description of the universe is as a Hamiltonian or perhaps as a Lagrangian, I'll give you that, it might be a Lagrangian, then we will have a list of models that we've made of the universe, each one that we've rejected over and over and over. We'll be left with an increasingly smaller list of models that are the ones that actually we think apply to the universe. So let me just say that. As we iterate through this process of observing, explaining, understanding, rejecting, we take this initial space of all possible explanations and we cut it down at each iteration to a smaller set of allowed explanations. So in the space of all explanations, we focus on, as we make better and better observations, we're left with fewer and fewer explanations that are consistent with everything that we've seen. That's the process of doing physics. Except humans don't want to reject hypotheses, humans want to confirm hypotheses. It's a sad fact, but it's a true fact. If you look at any social psychology experiment, you don't make headlines for rejecting the latest hypothesis, you make headlines for dramatic statements. So as time passes and we have fewer and fewer explanations that are consistent with all our observations, then we start to develop prejudices towards a certain explanation. On the basis of simplicity. Remember, always there is one explanation that's consistent with all the observations that have ever been performed. There's a guaranteed one, you get it for free. It's called the list of all the observational data that's been collected to date. So that's an absolutely consistent, complete description of the universe, the complete list of all observations. But you don't like it, right? Because it's not very simple. You don't get understanding from it. So there's something I should have emphasized here, is we want some notion of simplicity. It's very hard to quantify and define. And you can come up with notions like Kolmogorov complexity to quantify simplicity, but that's sort of not, that would tell us that sometimes that applying pk-zip to this list of data is a better explanation than that, but humans want something more, right? And I won't explain that. You know what I mean. And that's where I'll leave it. We want something simple. And so for us, for many of us, maybe if you ask a practicing computer scientist, they might say that a neural network is simpler. You know, I'm just saying for the physicists among us, the simplest explanation is you give a Hamiltonian a Hilbert space that Hamiltonian H in a Hilbert space curly H. You integrate Schrödinger's equation, and that's the simplest explanation for everything that we've seen, as long as it's consistent with everything we've seen. There it is. That's physics. That's what we do. But as I said, you know, we want to confirm hypotheses. We don't want to reject them, even though we're not allowed to. So as time passes, we focus in on inside the space of all explanations on certain points that we favor because they're simpler to us than just the list of all the data. And those are models that depend on unknown parameters. Okay, let's focus on the topic of simple explanations. For us in this course, and for most physicists I hope, they're going to be Hamiltonians that depend on some number of unknown parameters. And we even want that to be a finite list, right? It wouldn't be very good. We wouldn't consider it a simple explanation if we came up with a Hamiltonian that depended on an infinite number of unknown parameters. Because you'd still need to do an infinite number of experiments just on a counting basis before you could determine them all. So here these are the parameters, Z, J. We're going to make them elements of the real numbers just for the sake of this discussion here. And I'm going to put a lambda here. This lambda is going to be explained in a second. So a simple explanation is one for us in this course, and I would hope you would agree more generally, that a simple explanation is a model. A model is a Hamiltonian. It depends on some number of unknown parameters, Z1 through to Zn. And because it's a quantum, we're doing quantum mechanics here, although everything I said could apply equally well just to classical mechanics or to whatever comes beyond quantum mechanics if we don't live in a quantum universe. Everything I said still applies equally to any possible theory so far up to this moment. A model is a quantum Hamiltonian along with a Hilbert space, right? I mean, you can't have a Hamiltonian without a Hilbert space. And so lambda here, what is lambda? Lambda is just the list of the degrees of freedom that our explanation pertains to. I'll write it slightly differently. The list of the degrees of freedom that's what it is. Lambda is a list. Now, we don't know if that list is finite or infinite. I think we have some evidence that it's a finite list in the universe we find ourselves, and some evidence that it's not. This is the beauty of physics, right? We can actually, with a model like this, explain an infinite list of degrees of freedom with a finite number of parameters. That's possible. We can do that, right, if we have a good enough model. But for now, it's arguably correct that every explanation we have pertains to a finite list of degrees of freedom, right? Because we've made a finite number of experiments since records began. And we could explain all of that with a finite list of data, a very big one, but still finite. And so there's no particular reason to think that we have an infinite number of degrees of freedom in the universe. Or is there? And so this is the interesting point, that when we make predictions here, it's sort of this is somewhat vaguely formulated here, but one prediction you can make, for example, is that there are an infinite number of degrees required to describe all the observations we're ever likely to carry out. That's actually a prediction in itself, that we require an infinite number of degrees of freedom to describe the universe. It's one prediction. I wouldn't say we've rejected that hypothesis yet. The jury's out on whether it's finite or infinite. It seems very hard to design an experiment that would reject the hypothesis that we can explain everything with a finite number of degrees of freedom. But it's a hypothesis. Some people think it's simpler to assume an infinite number of degrees of freedom. Some people think that it's simpler to assume a finite number of degrees of freedom. I leave that to you, because I said I don't know how to explain simplicity. That's something that you have to come to terms with. So lambda may be finite or infinite. It's a bit premature. Now that we've got some notion of an understanding, I want to carry out this algorithm for this set of understandings, right? We have this set of allowed understandings here. So let's carry out the algorithm. Step 1, we make some observations. That gives us expectation values. For observables. So we get things that look like this. We get lists of expectation values. Of course, we get error bars as well. But let's just assume we can really pinpoint the expectation values. And then we want to explain the data. We want to understand it. How do we do that? Okay, well, we take all the models that we have that haven't been yet rejected, see what they would predict, and try and match that data. So you take these observations, then you solve each model, and then you make a prediction for these things here. If there does not exist, or if a particular value of these parameters here does not give the right answers, then you reject that model. You just reject it. It's gone. So what you end up with then is with a map from Z's to A's. This is our predictions. And usually this map is horribly many to one. There's multiple explanations. There's multiple z's and lambdas which can provide the same explanation for the observations we've made so far. That is a fact of life, and that's never going to go away. And this is an important point to dwell on. We have multiple explanations that are consistent with all the observations we've made so far. And I mean, this was clear from the outset, right? There's no doubt at least one Hamiltonian that explains everything we've seen so far. In fact, at the moment, the best model we have is linearized gravity, minimally coupled to the standard model. These words will make more sense to you towards the end of the course, with some cutoff. So that's a perfectly reasonable explanation of everything we've seen so far. It's sort of inconsistent with black holes, but then you can argue, have we observed black holes? But also the list of all data that we've recorded so far, that's again an explanation. You can even make that a Hamiltonian if you're particularly perverse. So we have multiple explanations for the same data. And we can't, these explanations, we can't make them go away. They're just there. But if we demand that our explanation is as simple as possible, and we give some notion of what as simple as possible means, then we can select out the right explanation. So the current winner. And this will change over time as we gain more and more data and more observations. So I'm going to give a tentative notion of what simplicity means in the context of high-energy physics, and then we'll work with that from now on. So firstly, the observation. So this list of numbers here, which are the predictions, which you get from the infinite power of being able to solve the Schrödinger equation. I mean, even coming up with this list is usually hard, but we've assumed that it's trivial for the purposes of this discussion. So here's an observation. This map is not invertible. It's many to one. There are multiple explanations for the same data. It's been present throughout this whole discussion. Right? You have the space of all explanations, you try and cut it down. You can never get, so yeah, you can never get one true explanation. So here's a list of expectation values. Here's the list of Hamiltonians depending on parameters. N is allowed to vary, lambda is allowed to vary. Each point in this space here is a different Hamiltonian, different Hilbert space, different number of parameters. And there's, for every point in here, a list of observations. There's multiple points that land on exactly that point. There's nothing we can do about that. It's just statistics. Many-to-one map. But we have a notion of simplicity, one that's been hanging around in high-energy physics for a good 100 years, and that is, one explanation is simpler than the other if it requires fewer parameters to explain everything, and it applies to more degrees of freedom. That's simultaneous. Or a model or explanation h lambda. So we can even use this as a definition, although I'm still going to insist on putting scare quotes around it, because it could be that Hamiltonians are not the right way to describe the universe. It could be that we could use tensor networks or something completely different, and that would end up being a more parsimonious description of everything we've observed so far. We just don't know. It's just so far this is what we've got. So a model here is simpler than another model with primes everywhere. So n prime can be bigger, smaller, whatever. If either n prime is less than, is actually bigger, so n is less than n prime, so it requires a fewer number of parameters to describe everything. Or it applies to more degrees of freedom, so the size of the set of degrees of freedom that the explanation pertains to is bigger, or both, right? So, ideally, we want a Hamiltonian that depends on 0 parameters and that applies to all the degrees of freedom that are required to describe the universe. That's the simplest explanation in existence. Now that's what string theory aims for, right? String theory aims to give that one true explanation, at least if you read the popular science discussions, the explanation which requires at most, say, 1 free parameter and it pertains to all degrees of freedom that are relevant for describing the universe. It's difficult to argue that that's the most simplest explanation possible. If you could do that, that would be pretty fantastic. At the moment, we're surprisingly close to this goal. I mean, it's absolutely astonishing, I think, given this sort of in principle infinite list of observations you might be able to carry out, that a finite number of parameters would do it all. That's kind of amazing. And we have a candidate that hasn't been rejected yet, and that's linear gravity coupled minimally to the standard model that requires a vast number of parameters, but it's a finite list of parameters to specify this. So that's pretty amazing. But imagine for a moment, sort of, if we lived in a different universe where the purely general relativity universe. So in this universe, we don't have quantum physics, we just have general relativity, and that governs everything. So it's a nice self-consistent theory. How many parameters would you need to completely determine the dynamics of general relativity then? Well, you may only need one, right? The cosmological constant. That would also be an alternative reality that we could have found ourselves in. That would be a very simple explanation. It's not the one we find ourselves in, but it's a good example of what could have been a good answer if quantum mechanics wasn't around. All right, so we have this notion of simplicity. This one's simpler, blah, blah, blah. Done, 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 right? Now we're getting there. Now we're actually going to try and carry out this algorithm in the context of quantum field theory. Let's try and carry out this algorithm in the context of quantum field theory. And that's the rest of today's lecture. I guess there's one point that I didn't emphasize that I should spend, actually I'll erase that and emphasize this one single point, because I don't think in this audience it needs that much emphasis, but I think if you read enough quantum field theory books, you might be confused by one certain point, one very crucial point. And it has to do with how we interpret these parameters. So the parameters Z1 through Zn, otherwise known as coupling constants, I mean, this was kind of clear from everything I've said before, and I've stressed this before, and you'll definitely have remembered me saying this from the last semester. These parameters here, these coupling constants, are not directly measurable. It's not always the case that there exists an experiment which directly measures the Z1. No. What you get is you make a list of predictions, you find out, you then compare your predictions with the experimental observations, then you invert this map. And this map here does not have to be linear, right? This map is usually horrendously nonlinear. And so that means that the process of getting the Zs from the observations is not an operationally well-defined step, in the sense that measuring the interpretation of these Zs is not necessarily operationally well-defined. We're using them to fit our data, so they have an operational significance there, but they're not themselves directly, I cannot describe to you an experiment which directly measures the Z. This is important if you want to attach the notion of an element of reality to this explanation here. So if you say lambda is the scattering cross-section, then you're attaching an operational significance to lambda, and then you'll be upset if lambda turns out to be infinity. Because you said, you believed for a while that coupling constant had an interpretation as an element of reality. So the minute you go down that road, the minute you say these parameters all are describing something real, then you will land up in real difficulties when you encounter infinities. But it's perfectly legal, as I mentioned last semester, to have parameters that are infinity that you require for explaining the universe. And I just hand you the example of the inverse temperature. So if you believe the universe is in a ground state, then the inverse temperature of the universe is infinity. You can still get finite predictions, but there's a quantity that's infinite. And we're going to see this happen throughout quantum field theory, that we're going to have to, in order to explain all the data we need, we're going to have to allow some of these parameters to go to infinity. But I claim that leads to no operational problems, because the predictions we make will always be finite. Yo, a question?
Yeah, you said that the numbers of parameters could be infinite.
Yes.
Infinity, but is there a way to So if you say we don't have infinity possible ways to measure something.
So I said, so the question is, if I interpret it, I said it was possible that we could have an infinite list of parameters, but isn't it possible, since we only have a finite list of observations, that we should just stick with a finite number of parameters? Yeah, you'll see, I'll try and explain that presently as we deal with divergences in quantum field theory, why an infinite list may still be necessary. And that's the kind of amazing parts of quantum field theory, where that can happen. Good. Quantum field theory. Let me summarize 2 points before I get to that. Okay, sort of trivial observation number 1, all predictions must be finite, otherwise your model is already dead and rejected. I hope that's kind of clear, right? If you ever predict infinity or a Grassmann number or a complex number or heaven knows a Banach space as the answer to a expectation value, then you know you've done something wrong, right? Because observations are never give us infinities. So all predictions must be finite. It is possible to give finite predictions with infinite ZJs. It's a second trivial observation. Just think of the inverse temperature, right? The inverse temperature can be infinity. That projects you into the ground state. The ground state can have finite, all expectation values in the ground state can be easily finite. And it's not hard to imagine that if, say, some interaction term was infinite, that might project you into some other sort of lower dimensional subspace of Hilbert space, but where all predictions are still yet finite. So these are 2 sort of simple points, but ones that can trip you up if you start ascribing too much operational meaning to the coupling constants themselves. And I would say that in 99% of all confusions about quantum field theory, that's where they lie, really, in this part here, where authors and people get very, very confused about the meanings of the coupling constants. And it's you know, they talk about divergences in the coupling constants as though that's a catastrophe. And it's not a catastrophe if all your observations that the model predicts are finite. All right, now to quantum field theory. We've encountered quite a few infinities along our journey in quantum field theory. Some of them could be just subtracted away on the grounds that they pertained to quantities that were not operationally well defined. So, like, for example, an infinite ground state energy it's easy to dismiss that in the context of non-relativistic, non-general relativistic settings. An infinite ground state energy, well, you can never observe the absolute ground state energy, so you're allowed to shift that without any operational consequences. That's how we can get rid of some infinities that way. Some other infinities took a little bit more hard work. Remember, we had these amputated diagrams, for example. And those are, again, justifiable on relatively simple grounds, that you're shifting things that you can't observe. However, in the last course, we encountered a real, true, honest-to-goodness, infinite predicted quantity, namely for the scattering cross-section. So I'm going to review that now, all of this in the context of phi-4 theory. But everything I say for phi-4 theory can be generalized to any other quantum field theory. So here our Lagrangian, which is equivalent to having a Hamiltonian in most cases, is this. And we spent a good number of weeks understanding how to compute Fs for phi-4 theory. So all we've been doing. Remember, all predictions must be finite. If a model gives you an infinite prediction, boom, it's rejected. And it looks like I've been teaching you about a model which must be rejected up to this point, because it's been giving you lots of infinities for things that you look around you and they're not infinite. So what is going on? Let's find out. So, point the first, right? You give yourself some credit. We spent a lot of energy computing these predictions. And we have encountered Fj equals infinity. Okay, what does that mean? Well, point the first, right? We've spent many weeks computing this, but not exactly, approximately. Could be that just our approximations are wrong. We're getting infinities because we're just doing wrong things. And you would certainly be allowed, you're entitled, and I think you should suspect the approximation method, since I've made it clear in all these derivations where we're perturbing unbounded operators by unbounded operators and so on. So there's lots of places where you might be well suspicious of what we've been doing, just on mathematical grounds. So it could be that the reason we've encountered infinity equals Fj for some operationally well-defined quantity, it could simply be that our approximation schemes are just rubbish. However, I think it's actually fair to say that over the past 50 years, we've got so many independent derivations of these infinities that one has begun, the general consensus is it's not in the approximation scheme that these infinities are there. It's that we haven't been talking about the models correctly. So that's for a fixed m and lambda we encountered. We encountered these infinities. And now you should begin to start to smell how the solution is going to work. So if we fixed beforehand m and lambda, we said, let's suppose that z1, which is m, is definitely this m, and z2 of lambda is definitely this lambda. Turn the handle of the perturbation machinery, boom, we get infinity every time, unless m and lambda are 0. But what was big lambda? We never really spoke about that. I mentioned it on occasion. Big lambda is the list of all the degrees of freedom we're trying to explain. And so far, with some exceptions, right, when I told you we have a cutoff, so far that's just been all momentum modes. Question?
Did we ever have a value for small lambda? I didn't remember, but we said that this lambda is fixed because we never.
The question is, did we ever decide on a lambda? Was it ever fixed? Well, implicitly we did, right? We said, given a lambda, here's what we would predict for the scattering amplitude. And we found that that functionally depended on lambda as infinity. So no matter what value of lambda we chose, that scattering amplitude was infinity, unless lambda was 0. So, but we do believe that there's scattering taking place. So we've already excluded the explanation lambda is 0. So lambda can't be 0. But then whenever we fix lambda with this calculational machinery we've had so far, we ended up with infinity with this scattering amplitude. Now, what I want to point out is that we were hopelessly ambitious. We were trying for not just a simple model, we were trying for, in some sense, the simplest model possible. We were trying for a model which was true for all degrees of freedom at once. Boom, done. But why don't we pull back from that ultra ambitious goal for a moment and say, let's try and explain all degrees of freedom up to a very large number, one that's far, far, far larger than anything we've observed so far. What's going to happen then? Well, that's what's called imposing a cutoff. Now, you could say this is admitting defeat, right? You know, I can't explain the whole universe, therefore we failed. Okay, this is patently absurd, right? If you can explain everything, every experiment that's ever likely to occur, ever, in the entire imaginable forward light cone of the human race, then it's not so bad. I mean, that's a pretty good result. And if you have a very simple model for that, then you should feel pretty happy about it. No. You would be more concerned if your explanation somehow gave predictions that depended on this arbitrary list lambda. That would be bad. So let's take it in turn. So what we should do we should deal first with the case where lambda is not infinity, right? This was just too ambitious. You can't run before you can walk. And that's called, in the business, that's called imposing a cutoff. We're just not going to attempt to explain all degrees of freedom with this very simple model. Now, there's one, there's some various questions that immediately throws up. How? It's totally arbitrary how you restrict to a finite degrees of freedom. That's problem number one. Problem number two. What consequences will this have for our predictions? Our predictions depend on on this cutoff. This would be terrible, right? If you came up with an explanation whose predictions depended on the size of the cutoff, so that on Tuesday, if you chose a cutoff of 10 to the 34 degrees of freedom, you got one prediction, and on Wednesday you chose 10 to the 35 degrees of freedom, you got a completely different prediction. This is super stupid, right? If your theory depends on an arbitrary parameter. So we're going to have to deal with that, right? And it's gonna, it's pretty clear from the first question that we're going to have to deal with something relatively fundamental here, because there's multiple ways to cut off a theory. There's multiple ways to say, I'm going to deal with a finite number of degrees of freedom. You could cut off in momentum space, you could cut off in real space, you could cut off in whatever, somewhere halfway between. You can softly cut off, you can hard cut off, there's an infinity of ways of cutting off a theory. And each of them will, of course, lead to consequences for these predictions here. Because functionally, expectation values depend on these unknown parameters plus the degrees of freedom you're trying to explain. But we're going to declare victory. We're going to now state the victory conditions for this game. We have one trick left, and that is that z's themselves do not depend, they're not directly observable. So they're allowed to depend on the cutoff. So we're actually going to declare victory if we can invert these functions here, the functions that give us the predictions, to get not like the one true coupling constant. We're giving up on that because we don't believe that these have a direct operational interpretation. No. We're going to declare victory if we can find a coupling constant that's consistent with all the observations we've made so far. And it's allowed to possibly depend on lambda. So the coupling constants, if we allow them to depend on the number of degrees of freedom we're trying to explain, and we can do that if we can still invert these maps, then we would declare victory. We'd have not one model, but if you like, we have a list of models. And as you add degrees of freedom, you have to change these not directly measurable quantities in order to match all the predictions you've made so far. But that's a small price to pay. Now, to be clear, not everyone is happy with this kind of cop-out. This is called effective theories, ones which can work for all degrees of freedoms that you're ever likely to measure, but which don't work for all degrees of freedoms. So notice the order of limits here. We first impose the cutoff. We work out the coupling constants as a consequence of that cutoff. We match all the, by matching all the experiments we've ever made. And then that allows us to make predictions up to this cutoff. But if we want to make predictions about degrees of freedom beyond the cutoff, should they be there, then we'd have to redo this process. So we haven't given a one true model for all the degrees of freedom of the universe. We've given a family of models for universes of arbitrarily large yet finite size. That's what this process delivers us. So some people are dissatisfied, find that as a not very satisfactory explanation.
Yeah, but does it mean that if I look at, say, a low energy mass of an electron, that is different from a high energy electron mass? Like if you say it depends on the cutoff, and we look at high energies cutoff, so the measurement will depend on the mass.
I'll try and paraphrase the question. Does it mean that our experiments will give different results for different cutoffs, I think is what you're asking. No, absolutely not. The mass of the electron is really 10 to the minus 19, isn't it? Yeah. 10 to the minus 31 kilograms, is that right? So where do I get 19 from? Charge. All right. It's really that. That's the rest mass of the electron. Boom, done, right? But the coupling constant that we call mass is not the mass of the electron. It's a coupling constant. That can depend on this arbitrary cutoff.
But that means that if we change the variable, that j, the function will not change, so we get another value of.
We'll get another value of this thing that we call the mass inside the Lagrangian, yes. Yeah. But that thing that we call the mass in the Lagrangian is not the mass. It's just a coupling constant that we have invented for our utility. And we noticed that in the low energy limit, it was equal to the mass. But that coupling constant, as I stressed here, is not directly measurable. You can't measure it in the limit of large interactions or for large energies. You can't directly measure m. You infer it by inverting this map, f. And this map is horribly nonlinear. It depends on this coupling constant m inside the Lagrangian in a horribly nonlinear way. And so when you invert it, then of course it can change. But the physical mass of the electron is what it was and what it always will be, unless this is changing as time passes, heaven knows. So that's why it's really, it's very unfortunate that we labeled those coupling constants with these letters, because it makes you think that they have an operational meaning. And indeed, you're so seduced into this by the low energy limit, where m really is the mass of the electron, or the scalar particle, the Higgs boson in this case here. But it's not. These two things diverge as you observe more and more degrees of freedom, as you probe higher and higher energies. The mass of the Higgs boson is really going to stay at 100 and whatever gigaelectron volts. I'm not good at remembering these numbers. But that coupling constant m inside the Lagrangian for the Higgs boson will be different at different energies, at different cutoffs. Should you be unhappy with that? Well, you would be if you called it the mass. But if we just use Z1 from the outset and said that Z1 is not directly measurable, then not a problem. Now, even with these relaxed victory conditions that I've just described here, it's still far, far, far from obvious whether or not we can ever satisfy them. It's far from obvious whether you can, by redefining a couple of parameters, be able to explain a list of observational data as you change lambda. It's just far from obvious. And in fact, I'd be inclined to have guessed that it was always impossible, just on the basis of counting. If you do a counting argument, it's clearly impossible. If you come up with an explanation for a finite list of degrees of freedom using some number of parameters, and then you increase the number of degrees of freedom that you can observe, then presumably anything could happen in those degrees of freedom that would therefore require more parameters to explain. There could be little fairies on pinheads at high momenta. There could be. We can't exclude that possibility. But that's not what this statement here is saying. This statement is saying that even with a fixed number of parameters, as we increase the number of degrees of freedom, we don't wreck through this dependence here the predictions we've already made. That's still totally non-trivial. And a theory which allows you to do this, to carry out this process here, is called renormalizables. It's a very special kind of theory. So a theory that allows you to absorb this cutoff here into redefining parameters while still matching a given list of data here, that theory is called renormalizable for a fixed number of parameters. Note the word fixed here, that's extremely important. It's trivial to do this if you allow the number of parameters that you need to explain the data to grow. So if you consider a larger set of degrees of freedom that you want to explain, and then you want to explain the data that you have already, then of course it's possible to do that if you allow yourself to have more free parameters to match. But if you constrain yourself to a given fixed number of parameters to explain the data you've already observed, then as you change lambda, since these functions are so nonlinear and horrible, it might be that you cease to be able to explain this data just by redefining a finite number of parameters. So it's not clear, it's not trivial that this is always possible with a fixed n. And so such a theory is presumably very special. It is a special theory. It's called a renormalizable theory. These are very remarkable objects in the space of explanations. Now, to do this all in QFT, so to do this in QFT for phi-4 theory, we usually focus on just one prediction, namely the scattering amplitude. There's, of course, an infinite list of possible predictions that a theory can make, but it turns out that just by focusing on this one here, you deal with all the other ones in one go as well. So this is a first astonishing, I think, fact about quantum fields, is that by focusing just on the scattering amplitude and possibly one or two more other operationally well-defined quantities, you can already prove that some theories obey the conditions to be renormalizable. And this is where some very interesting combinatorics comes into play. So this is what I want to do over the coming lectures, is to explain the combinatorics required to understand, the combinatorics required to prove that phi-4 theory, amongst others, is a renormalizable theory. It's a very astonishing property. It's not clear at all that that should be the case. So then let's now get to the tricky stuff. So the scattering amplitude, we get this from the S matrix. And last semester, I gave you the recipe for computing a prediction for the S matrix using phi-4 theory. And we know that there's going to be some Feynman diagrams here. A, B, 1, 2. Now, a Feynman diagram, as you remember, is just an integral I'm going to write out quite a few. Most of them go away. This is our prediction for the S matrix from 5-fold theory. You compute all the integrals represented by these diagrams, and you immediately get the answer infinity. Okay, some of those infinities can be gotten rid of by redefining parameters, namely the ground state energy, redefine it. You redefine the mass, this mass parameter, m, unfortunately called m, and then you can get rid of these ones. So lots of these infinities go away. The first infinity we can't get rid of by redefining the mass or the ground state energy is coming from these diagrams. So the first term where we can't get rid of the infinity by redefining the mass parameter or the ground state energy parameter is that diagram right there. I'm going to do it in momentum space for this discussion. We have one undefined momenta in this diagram. Yep. So that's the diagram, which is just an integral that cannot be, which evaluates immediately to infinity, this integral. And we cannot get rid of it by a simple redefinition of these two parameters here, E naught and M naught. That's a real honest-to-goodness infinity. And you can't even get rid of it by rescaling lambda. That's an important point as well. If lambda is not 0, that is infinity. So or I should say what this integral is actually equal to. Sort of important for a lot of what comes.
Sorry.
Yep.
Shouldn't that be the capital lambda?
No, that's little lambda. This is all so far for lambda is infinity. You know, let's be as ambitious as we can. So up to now, we were able, with lambda as capital lambda is infinity, to eliminate a lot of the divergences that we had. However, this is the first diagram where we're forced to say that big lambda is not infinity, because for any big lambda is infinity, we can't rescale lambda to get rid of that divergence. It doesn't work. The only rescaling that works is to set little lambda to 0. Then it's fine.
I'm a little confused. You said we should first, on the other board, you said we should first deal with lambda
Finite, yeah.
finite and goes cutoff. So
Yeah, okay, on the previous board, the question was, I said that we should start with lambda is not infinity and then work that way. I'm sort of not being quite consistent with the previous board here. So I'm trying to now remind you of, on this board here, I'm reminding you of the infinities that we encountered in the previous semester and to what extent we could get rid of them. And you know, there was something remarkable. We could get rid of most of the infinities still with big lambda being infinity. But the first point where we could not and where we're forced and where we should start with big lambda being not infinity, being finite, is this term at second order here. And I'll write out what that term is actually equal to. It's actually important for this discussion of how to rescale things. So if you apply the Feynman rules to this picture, then you get the following integral here. That's the actual evaluation of that Feynman diagram. It's this integral over one loop momenta k. And it may not be immediately obvious that it diverges, but just look at the denominator of the integrand. So it scales as k to the 4, little k to the 4, and the integrand itself scale is over 4, is d4k. So it's going to be basically a logarithmic divergence in this diagram. So if this integration range is infinity, then this will definitely be infinite. There's no way around it. It's really, really infinite. So we're going to, now is the moment we impose our cutoff. We say, okay, we were too ambitious. That was too much to ask that we could explain every degree of freedom that we've observed so far and every other degree of freedom in the universe. And we're going to do so by imposing a momentum cutoff. So as I said, there's a zillion different ways to impose cutoffs. Let's just choose one and stick to it. As long as our predictions do not depend on that cutoff, then we're happy. And the cutoff we're going to say is that we never ever try and explain a momentum degree of freedom with a value over this lambda. Lambda is now a number. This is a bit awkward. So lambda was a set up to this point here. Well, okay, no, let's stick with this, okay? Nah, that's not going to work. Bugger. All right. Yeah. This was inevitable. How about we just say KC? KC means K cutoff. So lambda is a set. It's a set of all the momentum degrees of freedom we're trying to explain. And Kc is our cutoff. It's a number. Some big number. So then if you do that, then this integral here, it's called the integral I. And this is a fantastic exercise. Hint. This is a fantastic exercise. If you do the integral with this cutoff in place, then you end up with this very remarkable result here. I mean, you knew it was going to happen, right? Because the integrand is 1 over k to the 4, and we're integrating d4k, so we're going to get logs. And what's s? S is just equal to k1 minus plus k2.
Sorry.
Yo.
We're gonna
Oh gosh, oh, it's KC, isn't it? Sorry about this. Yeah, that's true. It is fine to integrate over big lambda. You're absolutely right. Yeah. But we can't integrate. We can't have the answer depending on big lambda. It has to depend on KC, right? That's the maximum upper bound for K. Yeah, there it is, KC squared. So it depends logarithmically on KC. Well, actually, KC squared, which is, well, KC with an extra power of 2, extra factor of 2 out the front. And that's it, yeah. It diverges as KC goes to infinity. Now we want to play the game, right? And the game is, yo, a question?
What is the C after the I?
I'll C is some constant. It's a constant, you can work it out if you're really, you know, you have a bit of time. You can work at that. You can work out that constant, but it is a constant, right? And it won't diverge as KC goes to infinity. All right, so there it is. That's the answer. So now we want to play the game. Can we adjust our parameters Z and lambda, Z1 equals M and Z2 equals lambda, to eliminate that divergence? Because that divergence is not there in nature. We don't see scattering amplitudes scaling as the logarithm of some number that we chose on Tuesday to be 10 to the 34 and on Wednesday to be 10 to the 36. If you work it out, there's another exercise. So the amplitude for scattering at order lambda squared, when you sum all the diagrams up, you know, there's further diagrams with further divergences which you have to integrate, becomes scattering amplitude M, calligraphic M, is minus I lambda. Right, this is what we're used to seeing. Lambda is the scattering amplitude, but it's not, right? Plus, we get these other stuff. We get all these logs, depending on our momentum cutoff, KC squared. S equals K1 plus K2 squared. Sorry, there's a squared up there. These are the so-called STU parameters. At the moment, it's just, well, whatever. They're there. So M, the scattering amplitude, depends on the cutoff. Ooh, that's not good. That's really not good, right? So if you think of lambda as being one, little lambda as being one true value set at the creation of the universe, then this is the only conclusion you can draw and you have to declare failure. However, if you think of lambda as a parameter that we are fitting to match all of our experimental data, and then you realize that our hypothesis, our explanation, can depend on the number of degrees of freedom, then there is a way out. And this way out is to say that our explanation can be made fixed by allowing this free parameter Z2 equals lambda to depend on KC. And remember, with the relaxed victory conditions that I outlined a couple of boards ago, that's a perfectly allowed thing to do because Z2 has no direct operational meaning. It's a quantity, the actual scattering amplitude, which has an actual value that's actually fixed in an experiment once and for all, equals something that's not directly depending, is determined by a quantity that has no direct observational consequence. You can't directly observe lambda because every time you do a scattering experiment, you observe lambda plus lambda squared plus blah all the way up there. It's a nonlinear function. And how do we have to change lambda to depend on the cutoff to make that prediction fixed and equal to our experimental value? Well, we do the following, right? We say that we do an experiment, we measure mx, the scattering amplitude, do that experiment, and then we need that we need to allow lambda to follow Kc according to this equation here. We can actually do it. So as long as lambda depends on Kc in a way that solves this differential equation here, then it's possible to adjust lambda here to always be matching the experimental value for the scattering amplitude. So remember, lambda is just a parameter, it has no direct operational interpretation. So as you extend the domain of definition of your theory to apply to more and more degrees of freedom, you allow the parameters that it depends on to depend on the number of degrees of freedom. Why not, right? That's a good explanation. And as long as lambda depends on this cutoff on momentum Kc in a fashion that obeys this differential equation here, you're golden. You can explain all scattering amplitudes that you could have measured once and for all. Right, so that's where we'll stop today. But of course, you're entitled to still be quite skeptical because what I've done is one observational quantity, namely the exponential, the scattering amplitude here. And I've explained how I can at least get that to be, how to explain that with a changing parameter lambda. But what about 3-particle scattering, what about all the other experiments we could do? Maybe they depend on these parameters and we get infinities and we can't play this game and get rid of it, those infinities. Maybe that's the case. Amazingly, and this is really truly amazing, this is one of the most exciting results about quantum field theory, is that actually we can, by rescaling only m and lambda, or z1 and z2, we are actually able to make finite or near enough all the experimental predictions of the theory. That is an astonishing result and tremendously powerful, and I'll sketch how that works in the next lecture. Okay, but for now I thank you very much.